We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will introduce a new vector quantity, the angular momentum, that plays the role for rotations that linear momentum plays for translations. In particular, we will use Newton's second law to obtain the important result that the sum of the external torques acting on a system about a specified axis is equal to the time rate of change of the angular momentum of the system about that same axis. We will first evaluate the angular momentum for several different systems, and then we will apply this knowledge to determine the motion of systems in which the sum of the external torques is zero, which requires the angular momentum to be conserved. In our study of rotations, we have defined quantities that are directly analogous to those we have developed for translational motion, as shown in the table. We can see this correspondence directly in the expressions for translational and rotational kinetic energy and in the equations that determine the motions. We now want to introduce a new rotational quantity, the angular momentum, that corresponds to momentum. We know that it is a consequence of Newton's second law that if the sum of the external forces acting on a system is zero, then the total momentum of the system is conserved. We will define angular momentum in such a way that if the sum of the external torques acting on a system is zero, then the total angular momentum of the system will be conserved. We start by defining the angular momentum L of a point particle about some axis as the cross product of r, the vector from the axis to the particle, with the momentum vector. Taking the derivative of L with respect to time, we get two terms. The first term is zero, since the velocity vector, dr dt, and the momentum vector are parallel. The second term is just equal to the sum of the external torques on the particle. This equation, then, identifies the time rate of change of the angular momentum as the sum of the torques that act on the particle. Defining the angular momentum of a system of particles as the vector sum of the angular momenta of the individual particles, we obtain our desired result, that the sum of the external torques acting on a system is equal to the time rate of change of the angular momentum of the system. Therefore, if the sum of these torques is zero, then the time rate of change of the angular momentum of the system is zero, which implies that the angular momentum of the system is conserved. For the remainder of this pre-lecture, we will look at some specific examples that should help to give some concrete meaning to this new concept of angular momentum. Here we see a particle of mass m moving with constant speed v in a circle of radius r around some rotation axis. To calculate the angular momentum of the particle as it goes around the axis, we just need to evaluate r cross p. The magnitude of this cross product is just r times p, since the vectors are perpendicular. Using the right-hand rule, we see that the direction of the angular momentum is along the z direction. We can rewrite this magnitude of the angular momentum in terms of the angular velocity and the moment of inertia of the particle about that axis. Indeed, if we instead consider a collection of point particles, all having different masses and distances from the rotation axis, we can determine the magnitude of the total angular momentum of the system by simply summing the magnitudes of the individual angular momenta, and we arrive at the same general expression we obtained for a single particle, except that the moment of inertia now refers to the moment of inertia of the system of particles about the axis. This expression is really interesting. First, note its striking similarity to the expression for linear momentum, namely, the mass has been replaced by the moment of inertia, and the velocity has been replaced by the angular velocity. This correspondence is exactly the same as that we saw for translational and kinetic energy. What about the direction of the angular momentum vector? Applying the right-hand rule for r cross p for each particle, we see that the angular momentum of each particle, and therefore also the total angular momentum, points out of the screen. Now, this direction is exactly the direction of the angular velocity vector. Recall that we defined the direction of this vector to be given by a right-hand rule. Namely, if you curl the fingers of your right hand in the direction of the rotation, then your thumb points in the direction of the angular velocity. We therefore can summarize both the magnitude and direction of the total angular momentum by writing the simple vector equation that L is equal to I omega, where both L and omega are vectors whose directions are found by using the right-hand rule. We can extend our definition of the angular momentum to macroscopic solid objects by replacing the sum of angular momentum components over discrete particles to an integral over infinitesimal mass elements, as we have done previously in our calculation of the moment of inertia of solid objects. In fact, this integral is exactly the integral that defines the moment of inertia of the object about the axis of rotation. Therefore, we obtain exactly the same equation for the angular momentum of a solid object as we have derived for a system of particles, namely L is equal to I omega. For example, here we see a solid disk spinning with a known angular velocity about its symmetry axis. What is the angular momentum of this disk? Since we already know the moment of inertia of a solid disk about its symmetry axis, the determination of the angular momentum is easy. The magnitude of the angular momentum is just the product of the moment of inertia and the angular velocity, and the direction of the angular momentum is the same as that of the angular velocity. If the disk were replaced by a solid sphere, the expression for the angular momentum would look the same, except for the numeric factor of 1/2 would become 2/5 because of the change in the moment of inertia. In all cases, the angular momentum is proportional to the angular velocity. Now, what if the spinning object were itself moving around some other rotation axis? A good example of such a situation is the Earth, spinning around its own axis once per day while moving around the Sun once per year. The total angular momentum of the Earth about an axis through the Sun will be the sum of two distinct angular momentum components, one due to the motion of the center of mass of the Earth around the Sun, and one due to the rotation of the Earth about an axis through its own center of mass. Each of these two components is represented by a vector having a magnitude and a direction, and the total angular momentum of the Earth about the Sun will simply be the vector sum of these two components. Our focus to this point has been the calculation of the angular momentum of a system. We will now illustrate the use of this concept in examples in which there are no external torques acting on the system. Here we see two uniform disks having the same radius and mass, one suspended above the other. Both are free to rotate about the same vertical axis. The top disk has an initial angular velocity omega naught, and the bottom disk is initially at rest. The top disk is now dropped and lands on the bottom one. The frictional force exerted by the bottom disk on the top one opposes the motion and causes the top disk to slow down. The top disk, though, exerts an equal and opposite force on the bottom disk, causing it to speed up. Eventually, the disks reach the same angular velocity, and the two-disk system moves together with angular velocity omega sub f. Our task is to determine this final angular velocity of the system. The key here is to realize that torques that change the angular velocity of each disk are generated by the forces that the disks exert on each other. If we consider our system to consist of both disks, then these torques will be internal torques. Since there are no external torques acting on the two-disk system, we know the angular momentum of the system will be conserved. That is, the angular momentum of the system before the collision is equal to the angular momentum of the system after the collision. The initial angular momentum is equal to the angular momentum of the top disk. The final angular momentum is equal to the sum of the angular momenta of each disk. Setting these expressions equal to each other, we determine that the final angular velocity of both disks is equal to 1/2 of the initial angular velocity of the top disk. Now, this result is exactly analogous to the case of a one-dimensional, totally inelastic collision between two equal mass blocks in which one of the blocks is initially at rest. We can take this analogy further by comparing the kinetic energies of the system before and after the collision. We can write the kinetic energy of the system in terms of the angular momentum, which is the same before and after, and the moment of inertia, which doubles. We see that the final kinetic energy in this example is half of the initial kinetic energy, just as it was in the one-dimensional, totally inelastic collision. To this point, we have only discussed angular momentum in the context of rotating objects. Now, the angular momentum of a particle about some given axis is defined, though, simply as a cross product of the vector from the axis to the particle and the momentum vector of the particle. There is nothing in this definition that requires the particle to be rotating about that axis. Here we see a particle moving with constant velocity past an axis which is perpendicular to the screen. There are no forces acting on this particle. Its momentum is clearly conserved. Since there are no forces acting on the particle, there are no torques acting on it either, so that its angular momentum must be conserved also. If we now evaluate the magnitude of the angular momentum of the particle at any point along its path, we indeed see that we get the same value, namely, the product of its momentum with its perpendicular distance to the axis. The direction of the angular momentum vector at any point in the path points out of the screen. As this example illustrates, as long as there are no external torques acting on the system, the total angular momentum of a system is conserved even if the object is not moving in a circle. On the next slide, we will solve a simple problem that involves both the angular momentum of rotation as well as the angular momentum from motion in a straight line. Here we see an empty merry-go-round at the playground. You decide to take advantage of this opening and take a run at it and jump onto its outer edge along a path that is tangent to the edge. How fast will you and the merry-go-round end up spinning after you've jumped on? To answer this question, we will define our system to consist of you and the merry-go-round. We will choose the rotation axis to be the axle at the center of the merry-go-round, and we will assume that the axle is well greased so that we can ignore any friction when the merry-go-round rotates. With this assumption, we can say that there are no external torques acting on the system. Therefore, the total angular momentum of the system must be conserved. On the last slide, we determined how to calculate your angular momentum about the rotation axis before you jump on. Namely, this initial angular momentum is just equal to the product of your momentum and the closest distance that your path passes from the axis. After you jump on, both you and the merry-go-round rotate with the same final angular velocity. So the final angular momentum of the system is equal to this angular velocity times the total moment of inertia of the system. The total moment of inertia has two parts, one due to the merry-go-round and one due to you. To determine this moment of inertia, we will take the merry-go-round to be a uniform disk of known mass and radius, and we will treat you as a point particle at the edge of the merry-go-round. Since the angular momentum of the system is conserved, we can set the initial and final angular momenta equal to each other to obtain the final angular velocity. To get a feel for some magnitudes here, let's take your mass to be 75 kilograms, your initial speed to be 2 meters per second, and the mass and radius of the merry-go-round to be 150 kilograms and 2 meters respectively. For these numbers, we find that the final angular velocity is half a radian per second. We conclude with a brief discussion of the main points of this pre-lecture. First, we define the angular momentum L of a point particle about some axis as the cross product of r, the vector from the axis to the particle, with the momentum vector of the particle. We extended this definition to a system of particles by defining the angular momentum of the system to be the sum of the individual angular momenta. For a system of particles that is rotating about an axis with a fixed angular velocity, the angular momentum of the system can be written simply as the product of the moment of inertia of the system about the axis and the angular velocity vector. Second, we use Newton's second law to obtain the important result that the sum of the external torques acting on a system is equal to the time rate of change of the angular momentum of the system. Consequently, if the sum of the external torques on a system is zero, the angular momentum of the system is conserved.